Thank you to the organizers for this chance to talk. I will talk about classifying modular tensor categories. I will first give a brief introduce for the definition and some examples. Then I will try to give a short overview about the classification problem for modular tensor categories. And then I will talk about some general property for modular tensor category that's useful for the classification. And finally, I will talk about some results based on the joint work with Richard Ng, Yilong Wang, and Julia Pravinik, Andrew Chopre, Zhichang Yu, in two separate papers. Okay, so we say a pre-modular category over complex number C is a spherical braided fusion category. So the spherical structure and the braiding gives this ribbon structure, which is a natural isomorphism of the identity functor to itself. So for any simple object, this ribbon structure on this simple object by Schur's lemma, it's a non-zero scalar multiple of the identity. So we record for all the simple object, we record this complex number into this diagonal matrix T. By Wi-Fi's theorem, this T matrix is of finite order. And given two simple objects, one can take the trace of the double braiding like this. First, you braid X star with Y, and then you braid Y with X star, and you take the trace. So for every pair of simple objects, you get a complex number. So we collected these numbers into the S matrix. So we say a pre-modular category is modular if S is invertible. And this pair of matrices S and T is called the modular data for the modular tensor category. Here are a list of some examples of modular categories. The first one is you take an abelian group A and with a non-degenerate quadratic form on A, this gives the pointed modular tensor category. And they can also be constructed from finite groups. So you take a finite group with a 3 cocycle, and you can see the twisted quantum double. You take the representation category. This will give us a modular tensor category. These are the some examples of integral modular tensor category, which means the dimension of the simple objects are integers. They can also be obtained from quantum groups. Consider a finite dimensional semi-simple Lie algebra, and we consider the quantum group with Q a formal variable. And at a certain root of unity, we consider the representation of quantum group, which is a ribbon category, and take a suitable quotient, you will get a modular category. Since I have a over-ambitious title for my talk, so I guess I should have at least a few slides towards a different aspect for the classification problem. So the first one direction I want to mention is the classification by rank. Okay, so for modular tensor category, the rank finite theorem told us that given a fixed rank, there are only finitely many modular tensor categories. And the rank less or equal to 4 was done by Eric Rowe, Richard Stone, and Zhang Wang in 2009. Okay, and the next rank equals to 5. Up to fusion row, it was done by Paul Bluya, Richard Ng, Eric Rowe, and Wang in 2016. So in between this, in between 2009 and 2016, there was result which we call the congruence subgroup result proved by Richard Ng and Schoenberg. Which states that, which basically gives you a bound on the modular data. So compare with rank 4, SL2Z representation theory was used, which I will talk about more detail later. And this year, Richard Ying, Eric Rao, Zhang Wang, and Xiaogang Wen, they complete the classification of rank 6 up to modular data. So the technique they used is roughly they consider the irreducible representation of SL2Z, and they consider which ones can be realized by the modular tensor category. Okay. So they have some general results, and as application, the rank 6 is complete. So the next direction, which I was involved, is inspired by this low rank classification. So in the low rank classification, the Galois group action on the modular data was used. So one gets a lot of symmetries on the modular data. So so we want to ask the following question: can we just classify modular categories by the number of Galois orbits? So as the first step, we consider the following extreme case with Ying and Yilong Wang. So these two ones are different people. So we have a classification for the case of orbit equals to 1. And with Julia, Andrew, and Zhiqiang, we consider the Galois action interact with the fusion subcategories. And as application, we have some partial result when the orbit equals to 2. So roughly speaking, we have the Deligne tensor product structure for the modular tensor category with orbit 2. So another direction towards the classification of modular categories is consider the weak group. Okay, so the weak group is defined in terms with a Brady fusion category not necessarily have the spherical structure. So Brady fusion category is called non-degenerate if the Mueller center is trivial. Okay, so so another definition for modular category is a pre-modular category with non-degenerate breeding. So this result, which is equivalent as defining the non-degenerate as matrix. This is proved by Mueller. And we say two non-degenerate breeding fusion category are weak equivalent if up to tensoring with a dream field center of some fusion categories, they are braided equivalent. So the set of weak class of modular tensor category forms a group. And the multiplication is induced by taking the Deligne tensor. And the unit elements in the group are the class of dream field center. And for the class of the inverse of the class of category C is the class of C reverse, which is category C with a reverse breeding. This gives us an infinite abelian group. And there are studies about the structure of the weak group and the pointed modular tensor category is actually forms a subgroup of the weak group. And in this talk, we won't focus on this direction. So I just mention it as some of the general direction towards the classification. So there are other directions for the classification of modular tensor category in terms of the factorization of the dimensions. This is perhaps not all the list that's completed here, and I apologize about that. And of course, this is not a comprehensive description of all the classification of modular category that is going on. So there are other directions. Okay. Next, I'm going to talk about two properties of the modular tensor category. One is the SL2Z representation. The other one is the Galois group action, which are essential tools for our study in these two projects. So the first one is the given the modular tensor category, and we consider the anomalized modular data SNT. And there are some relations in terms of SNT. The S to the 4 is a square of the dimension times identity, and the ST cubed is a scalar multiply S squared. So here, this P plus minus is computed this way, which is called the Gauss sum of the modular category. And let's consider the group SL2Z, which has two generators, which can be generated by the following two elements. Well, S is this off-diagonal matrix, and T is this upper triangular. And the defining relation for S and T is the following. So if we send the generators of SL2Z to the modular data like this gives us a projective representation. We call it a rho bar C of SL2Z. And by Ng and Schoenberg in 2010, they showed that if N is the order of the T matrix, then this projective representation has kernel or congruent subgroup of SL2Z. As a result, the image of this projective representation factors through SL2Z mod N. So in particular, the group generated by the modular tensor category, modular data SNT is a finite group. Also, if we consider, so I use this notation Q adjoining S as the field extension. If you take a rational Q with all the entries of S, this sits inside of the cyclotomic field of order N, where N is the order of the T matrix. I guess it's worth to mention here that in the study of conformal field theory back in the 90s, Du Bois and Gori, they showed that the Galois group of this Q adjoining S is abelian. So by the Kronig-Webb theorem, they know that this field extension Q adjoining S is contained in some cyclotomic field, but it's not clear what is the bound, and this result tells us the bound, it's actually bounded by the order of T. So this projective representation can be lifted to a linear one. So in this talk, we will consider about the Foley lifting. So we normalize the modular data S and T. So we normalize S by the square root of the dimension, and normalize T by this number gamma, where gamma is any third root of the multiplicative central charge. There are other ways to lifting, and up to tensoring with a character of SL2Z, they are all equivalent. Okay, so now we take the generators to the normalized modular data. This gives us a linear representation of SL2Z. And it was proved by Dong, Lin, and Ying that this linear representation factors through SL2Z mod N. So here the little n is the order of the normalized T. So the also the image sits inside of this general linear group. Here R is the rank of the category. Okay, so now we know that the field extension of Q adjoining the entries of S sits inside of this cyclotomic field, and it's an abelian extension. And from now on, we will call this Galois group of Q adjoining S by GC. And by the Verlinde formula, there's a one-to-one correspondence between the simple object of the modular tensor category and the characters of the fusion ring. So here character means a ring homomorphism from the fusion ring to the complex number. And so the character is given by following. So for any simple object y, it gives rise to a character that sends x to sxy divided by the dimension of y here. So since it's a one-to-one correspondence, if we take any Galois element of the in the Galois group, so this sigma permutes the characters. So if we take sigma acting on this sxy divided by s1y, there's a unique permutation on the simple object such that it's like acting on the simple object y. So that's a Galois action on the entries of S. So this is just copied down from the previous slides in case we forget. Okay. So moreover, if we take any Galois element from the cyclotomic field extension Galois group, and for any simple object x and y, we have the following relation. So I guess this one, Terry already write it down on the board. And the second one is if you take Galois elements acting on T twice, and you end up with a permutation on the simple object. Okay, so basically this Galois group action gives us a lot symmetries on the modular data. So for the low rank classification, so once you assume the Galois group, and one gets a lot of symmetry on the SNT, and this is how they one of the tools they used for low rank classification, especially for rank 4 and 5. So as an exercise, let's take a look at an example. Okay. So let's think about an Ising modular tensor category. So the S matrix is given like this way. So if we rewrite them as dividing, basically you're dividing the dimension on each column. And if you look at the entries, you can probably guess how the Galois group element acting. And we know that Q adjoining S is the same as Q adjoining square root of 2. And the Galois group is isomorphic to Z2. And the non-trivial Galois elements acting on the S entries, basically they permuting the first and the last column and fix the middle one. So that's basically the basic two tools we're going to use. One is the representation of SL2Z, and the other one is Galois action in our study for this talk. So I guess right now we're ready to talk about the classification in terms of the Galois orbit. So first we want to consider when the orbit is 1, and this is the case when the Galois action is transitive. So we call a modular category is transitive if the Galois group acts transitively on the set of irreducible set of simple objects. So let's take a look at the first non-trivial example, which is the Fibonacci category. It has two simple objects labeled by 1 and tau. Okay, the fusion rows is generated by tau tensor tau, and the S matrix can be written like this. So if we just follow the similar exercise as before, we rewrite the S entries like this. And notice that Q adjoining the entries of S is the same as Q adjoining square root of 5. And the non-trivial Galois elements acting on the S entries by permuting these two columns. Okay, so basically this gives us a transitive action on the set of simple object. Okay.
One is centered tau and tau centered.
One is centered tau. Yes. Okay, so it turns out that the transitivity is a strong condition which implies a list of results that can make the classification possible. So I list a few of them, and I will go through them one by one. Okay. So our first kind of essential observation is that being transitive gives us the irreducible representation. So the statement is as following. So if we have a transitive transitive modular tensor category, then the corresponding modular representation is irreducible. So why we think about this result is important. So first, to recall that the linear representation factors through SL2Z mod n. Well, n is the order of the normalized T. And by the Chinese remainder theorem, we can break up this group SL2Z mod n to SL2Z mod prime powers. Okay. So also the irreducible representation of SL2Z mod prime power is known. So it dates back to 1976 by Nobs and Wolfram. So another important observation we have is that transitivity implies a fixed point free. Okay. In particular, we have the following result. If the modular tensor category is transitive, then the order of the Galois group is the same as the rank of the category. Okay, so this is in fact because that the Galois group is abelian, and a transitive abelian action is also fixed point free. So the Galois group acting on the modular tensor category freely and transitively. So as a consequence, we have the group order is the same as a rank. So this result also gives us a criterion for checking if the modular category is transitive or not. So let's take a look at an example. Let's consider Fibonacci tensor with itself. So the S matrix is just to take the tensor product of a chronic tensor product on the matrices. So the Q adjoining the this fib tensor fib is the same as Q adjoining square root of 5. So we know that the Galois group is Z2. However, the rank of this category is 4, which is not equal to 2. So fib tensor fib is not transitive. So it's natural to ask here, when is the Deligne tensor product transitive? So we ask the following question: if you have two modular tensor category, when their Deligne tensor product is transitive. And this can be answered as the following. So if you have two modular tensor category and their Deligne tensor product is transitive, if and only if both of them are transitive, and if you consider the field extension of Q adjoining dimension of C intersect with Q adjoining dimension of D, they are trivial. They have trivial intersection. So as an application of this corollary, let's construct some transitive modular tensor categories. So let's consider another example of transitive modular tensor category is PSU to level 5. It is a rank 3 modular tensor category. It has simple objects labeled by 1, alpha, and beta here. And the fusion rows is given as the following. And the S matrix can be written like this. Well, the alpha is this 2 times cosine pi over 7. And we can do the same exercise as before. So you can rearrange the columns of S. And one can show that this modular tensor category PSU to level 5 is transitive. So by the previous result, since Q adjoining square root of 5 intersecting with Q adjoining this D alpha is trivial, so we can conclude that the Deligne tensor product is transitive. Okay. So in fact, Fibonacci is also in this series of modular tensor category. It is PSU2 level 3. Okay, so maybe it was to take a look at this PSU2 level something. Okay, so these are subcategories of SU2 level P-2. Okay, so SU2 level P-2 from the rep as UQSL2, where Q is 2p root of unity, and P greater than 3 is a prime number, and the simple objects are labeled from 0 to P-2. So there are P-1 simple objects, and this is an example of the fusion rows. And however, this modular tensor category is not transitive. The reason is that there's a simple object if that is invertible. So basically, you tensor it with itself, you get the unit object. And the transitivity is a condition that implies that we cannot have a non-trivial invertible object. So we consider taking some subcategory by throwing this simple object away. So for SU2 level K, SU2 P-2, if you look at the fusion row, there's a Z2 grading. So in particular, if you look at this simple object, this belongs to the non-trivial grading. So that's how we throw it away. So basically, we take the adjoint subcategory of SU2 level P-2. So that gives us PSU2 at this level. And we call that Fibonacci is an example that's corresponding to P equals to 5. And the simple objects are those objects from SU2 with even labels. This is an example of the fusion row. And one can explicitly write it down their modular data here. Sij is indexed by I and j in terms of quantum integer, and for t can be presented this way. Okay. So to prove that this category is transitive, it suffices to show that for every simple object lives in the orbit of the unit object. Okay, so we can rewrite the entries of S like this way as before. So this gives us this quantum integer. And to show this category is transitive, so notice that 2p is relatively prime to 2j plus 1. So there's for any j, there's a Galois element that sends 0 to j. So every simple object lives in the orbit of 0. So this is an example of a transitive category. Moreover, this category is a prime category. So a prime modular category. Prime modular category means that there's no non-trivial modular subcategory. Okay, so how to show that? One observation is that this category is generated by the simple object labeled by 2k. So it is, so therefore it is a prime category. Okay. So one can change the root q by another primitive 2p root of unity, and we call this resulting category a Galois conjugate of PSU2 level P-2. And this is a result by Froelich and Kerler in 1993 that if C is a modular category that has the same fusion role as PSU2 level P-2, then C is equivalent to a Galois conjugate of this category. Okay, so this is actually one of the connecting one of the building blocks in our proof of the full result. So finally, to put everything together, we need to use the property that transitive modular category has, which is a unique factorization. So modular tensor category, recall that a modular tensor category is a prime if every modular subcategory is equivalent to itself or back. And it's a result by Mueller that every modular category is equivalent to a finite Deligne tensor product of the prime ones. Okay, so but it's not always true that the factorization is unique. There's one case that we know that it gives us the unique factorization is that if the pointed subcategory is a trivial, the prime factorization is unique up to a permutation of factors. Okay. And recall that, as we mentioned before, for transitive modular tensor categories, they have the C pointed is trivial. So moreover, we have the following result. If C is a transitive modular category, then every fusion subcategory is transitive modular. Also, basically from the C pointed is trivial, the prime factorization is unique up to permutation of factors. Okay, so so let's put everything together. So we have the following classification for transitive modular tensor categories. So basically, if C is a non-trivial prime transitive modular tensor category, then C is equivalent to a Galois conjugate of PSU to level P-2. Okay. So roughly speaking, so to get to this point, first we need to start from the representation. So recall that transitive modular categories gives us irreducible representation. So we study the result from the classification of SL2Z mod prime power, and we study the image of the SNT, and then we end up with the category must have the same fusion role as PSU2 level P-2, and then we use the result by Froelich and the Curler, and we get to this classification for prime transitive ones. So combining this with a decomposition for transitive modular tensor category, we have the classification for all transitive modular tensor categories. So basically, if C is a non-trivial transitive modular category, then C is equivalent to a Deligne product of prime ones. And recall that we need to be careful when we put them together. We need to make sure that their field extension is trivial. So that requirement actually reduced to they need to have distinct order of T matrices. So I guess I went too fast. Sorry about that, but maybe we can have an early lunch. So, so as one step towards the second case, which is when the Galois group has orbit 2. So let me first show some examples. So this is a list that we know that the Galois group has orbit 2. So the first one is an Ising category, which we already checked. And there are some low rank examples. And the rest of 3 rows are infinite family of modular tensor category with orbit 2. So the first one is a pointed category. So basically, if you look at the orbit size, so the first column is fixed, and the rest of the column are permuted by the Galois element. And there are 2 other infinite families, which are also a simple modular tensor category, which means that they have non-trivial fusion subcategories. So these are the examples when we study the Galois group with orbit 2. Okay, so So in this paper with Plavenik, Schupere, and Zhichangyu, we studied the Galois group action interact with the fusion subcategories. We have some general result, perhaps can be applied to a bigger orbit size. And as an application, we can characterize how the Deligne, what is the Deligne tensor structure for orbit 2. So basically, if C is a modular category with orbit size 2, then C can be factored this way. So I cannot push them together into a diagram. Okay, so we consider two separated cases. So the first one is the pointed part is trivial, and the second one is non-trivial. So here T represents the transitive modular tensor category with certain restrictions. And when the pointed part is trivial, this modular tensor category D is either a simple modular tensor category with orbit 2, or is a Deligne tensor of some Fibonacci category. Also, we need to be careful when we put them together. We need to have some restriction on their conductor, which is the order of the T matrix. So when the pointed part is non-trivial, so then this category D is a pointed, which we saw before, of prime dimension. Also, or an easy modular category, which is the first row of the list of the examples. And here T is transitive modular. Also, we need to be careful when we put them together, so we add restrictions on their conductors. Okay. So as you can see from here, this problem of classifying the orbit 2 now is reduced to the classification of simple modular category with orbit 2 under this result. Okay, so I guess that's all I want to talk about today, and thank you for your attention.
The questions?
The knowledge of the theory has particularly playing a big role in the tensorial as I do, or has everyone tried implementation theory of other mapping classes?
I'm not aware of that. Maybe. Yeah. Sorry, I don't know about that. Yeah.
No more questions? Yeah, there's one.
So you don't have like finiteness by number of orbits, but do you know if after some like finite number you do get that?
After some finite number.
So you show like for 2 Galois orbits you can have infinite, like you have an infinite family of modular things with that number of orbits. Is that right?
Yeah.
So the question is there any finite number of orbits after which you know you will have only finitely many classes with that number of orbits?
I guess I don't know. I don't
Okay.
think so. Yeah.
Okay.
You can always take some transitive prime category and tensor with it and get another one of the.
Oh yeah, because
Oh.
the transitive is an infinite. Yeah.
You can ask the question more simple.
There's don't seem to be more questions, so let's thank Qing again.